Welcome learners to today's program, and my name is Shashank Srivastava, and I am from the School of Engineering and Technology, Indira Gandhi National Open University. So today's topic I have taken up is Introduction to Measurement and Metrology. Actually, there is a course named Measurement, Metrology and Tribology, which comes under the program Certificate in Condition Monitoring, which is being offered by the School of Engineering and Technology. So that's why I'm taking up this particular program or course, we can say, and it is named Introduction to Measurement and Metrology. So I'm taking a part of that particular course. It's a beginning, you can say. So what do we understand by measurement actually? See, there are different quantities of different substances which we use in our daily life, or you can say we have certain lengths or weights, you can say. So how can we define them? So we define them by a certain process or a method, and that's why we use units also. And when we do these kind of things, then it is known as measurement. So investigators are there in different parts of country who want to compare the results of the experiments, various experiments which take place in various laboratories and research work that takes place. So they want to compare with certain standards. Like suppose I say that a certain length is there, which is around 10 kilometers. So I am specifying that it is 10 kilometers. So that has to be again standardized, and it has to be measured with certain standards. That's what we refer to as measurement. So there are certain institutes which are doing these things. Like in the US, we have the National Bureau of Standards, which is the prime body for looking after these kind of measurement aspects, and it maintains the standards in the United States. Similarly, in India, we have the Indian Standard Institute, which is based in New Delhi itself, and it has taken up the responsibility for maintaining all the standard measurements. So to monitor the standard of measurements, we have also the institute, the same institute, which is Indian Standard Institute, which issues instructions to put the ISI mark. You may have seen in various objects which you may be using in daily life or in your office also, where we have got certain objects which have the ISI mark. Like for example, you use iron or press to press your clothes. So it has got a ISI mark. So by that way, you know that this thing is standardized and it will not harm you. It has got a certain standard. The mark has been placed on that, and that is the ISI mark. And in that way, we compare it with non-standard objects also. Then what is metrology? I have talked about measurement. So what is metrology? Metrology is defined as the process of making extremely precise measurements of certain relative positions and orientations of different optical and mechanical components. Like suppose I have a car and I have got a reference. Suppose I have placed my reference at the back end of the car. Then if I want to know where is my engine, where is the engine of the car, then using that reference, I will measure the distance from the engine to the back end of the car, and in that way I will be able to say that this is the distance or the relative position of the engine with respect to the back end of the car. So that is what we are doing in metrology. And the study of measurement actually involves measuring quantities. Like I told you, like I'm measuring certain thing in kg, in terms of kg, or in terms of liters. So I'm measuring, like I measure how many liters of milk are there. So that way, it is a quantity. And then we use measurement in calibration of the instruments, and also in determining the uncertainty of a measurement and studying the weights and measures or measurements. Then engineering metrology. I defined a general term metrology, then engineering metrology. It is somewhat restricted in terms of the quantities which we measure, like length, weight, time, temperature, angles, and other quantities, which are usually expressed in linear or angular terms. So for every kind of quantity measured, there must be a unit to measure it. Like suppose I am saying that I talked about distance. So I am saying how much distance, how will you specify that thing? So I will define it in terms of meters or kilometers. So that unit is very, very important. Otherwise, how a person will tell that, okay, it is 10 kilometer or 5 kilometer, or it is 5 kg or 10 kg. How will we specify? So unit is a must for knowing how much quantity we are going to define. Further, in order that this unit is followed by all, there must be a universal standard, and the various units for various parameters of importance must be standardized. Because if we are not standardizing the thing, suppose I am sitting in India, somebody else is sitting in US. So that kg, if I say kg, so the 1 kg should be same in India and 1 kg should be same in US also. So as soon as I say 1 kg, it should be same throughout the whole world. That's why we have to standardize the thing. If I say 1 liter, then it is 1 liter in India and 1 liter in US or UK, anywhere else in this world. So that's why standardization is very, very important. It is also necessary to see whether the result is given with sufficient correctness and accuracy for a particular need or not. Because if suppose I do a measurement, if I make a measurement and I am getting a faulty reading, then there's no use of measuring it, because it will change our results and it can give catastrophic results as well. So that's why the accuracy of the result is very much important. And this will depend on the method of measurement and the measuring devices that we are using. So when we talk of measurement, I also talked about how if the measurement is not accurate and I am not getting the proper reading, then obviously that means there are certain errors. So now we are going to talk about those errors. So what are the errors that we generally see actually? So some are there, like they are random in nature. Some may be due to gross blunder, very common mistake that happens, or human error on the part of the experimenter, and others will be due to some unknown reasons which are beyond our scope, or we can say which are constant in nature. So the first error is the gross error. The number B, as we say, is the systematic error, and C is the random error. So let's first of all talk about the gross error. So these errors are a kind of a blunder on the part of the experimenter or the observer. The person who is doing the experiment or who is observing that particular reading in a machine, he makes a certain error. And these errors are caused by mistake in using the instruments. Like suppose I am measuring length with the help of a vernier calipers and I don't know how to use that particular vernier caliper, then there will be mistake. Or the error may be due to faulty recording of the data. I have made the measurement correctly, but I have recorded it wrongly. So that can be another case. And then finally, if I am making certain calculations and those calculations go wrong, then also there may be a mistake in measurement. So all these kinds of error come under gross errors. Now I am giving certain examples. Suppose I am measuring pressure with the help of a pressure gauge, and the reading is like 1.01 Newton per meter square. But I record it as 1.10. While writing down, I write it down as 1.10. So there's an error of 0.09 Newton per meter square. So this is a gross blunder. Similarly, somebody may have a habit of memorizing the data. Like I measured this particular pressure. Similarly, suppose force is there. So I say 10 Newton force was there. But then I said, no, I will not write it down. I will write it down later, and I'm just memorizing it. I will keep it in my brain. So I kept it like that. And when I went after some time, when I went and wrote it down, then I wrote it down as 11 Newton. Instead of the 10 Newton, which was the correct reading, I wrote down as 11 Newton. So that blunder again has occurred because my memorizing power was not that good. So this is another kind of error in the data. And then errors again due to the calculation in the results, calculation mistakes. So there will be error. Another gross error arises when an experimenter makes use of an ordinary flow meter having poor sensitivity to measure low pressure in a system. That means I have to measure pressure in a system and I am using the wrong instrument. I am using a flow meter to measure the pressure. That's a gross blunder. So these things can also happen, meaning taking up the wrong instrument to measure certain other parameter. And then after talking about the gross errors, now we move on to the systematic errors. So these are inherent errors of apparatus or method, meaning the apparatus itself is in itself is not that good. There is certain fault or inherent error in it, even if there is no gross error on the part of the experimenter. So these errors, due to their fault in the instrument itself, they will always give a constant deviation because the error is inherent in the instrument. It is not on the part of the experimenter or observer. So there are certain classifications of these errors. The first one is the constructional error. None of the apparatus that has been constructed till date will satisfy all the specifications completely. Why it is? Because the humans have that tendency, we are not perfect. So whatever we are constructing also is not going to be perfect. Yes, we try to achieve perfection as much as possible, but we cannot say that it is always 100%. And this is the reason of giving one thing, that is guarantee within a limit. Like we specify certain range. Like if I say that I am measuring pressure, then I say it is 10 Newton per meter square. So when I will specify that, it will be given as 10 Newton per meter square plus 1 or minus 1 Newton per meter square, meaning there is a certain range. Therefore, manufacturers always mention the minimum possible errors in the construction of the instruments. So whatever minimum is possible, we try to manufacture like that, and then we mention it in the specifications. So this is the constructional error. Then we have got the errors in reading or the observation, like the construction of the scale. Okay, suppose you have made a scale, like we have I can talk about a simple scale for measuring length. So the divisions that are there of the scale, if they are not very good, or when you are viewing it, they are somewhat blurred, so it will not give a good reading. So that error is happening because of the faulty construction of the scale. The reading will not be uniform and clear. Then B is the fitness and the straightness of the pointer. The pointer should be very, very sharp, and it should have a straightness. Otherwise, there are small divisions in the scale. And you may not be able to know which division it is referring to, where the pointer is going, if the pointer is very vague or it is not sharp. So it has to be fine and straight, then only it always gives the error in the reading. So following are some of the reasons of the errors in result of the indicating instruments. One is the parallax. Like suppose if I am not viewing a certain scale directly from the top, but perpendicularly, then due to a certain angle there will be an error in that particular reading, and that is known as the parallax error. And then the D1 is the efficiency or the skillness of the observer. So if the observer or the experimenter is not that efficient, he may record a wrong reading, or he may not be able to gauge out what the instrument is saying, what kind of reading it is giving. So it is largely dependent upon the skillness of the observer by which reading is noted accurately. Then we have got the determination error. It is due to the indefiniteness in the final adjustment of measuring apparatus. Like for example, suppose there is maximal bridge, so here sound is being used. So one observer may hear the same sound in a different way, the other one may hear differently. So we cannot make out what is the reading or how much decibel the sound is off. Then we are not able to make out that thing, because it is differing on the basis of the person. So that is called the determination error, because we are not able to determine how many decibels that sound is carrying, because one person is hearing somewhat different, the other is hearing. So it depends on the hearing capacity of that person. So it is a determination error. Then we have got the natural error of the method errors in measurement. No method is perfect, as I talked about earlier, that no instrument is perfect and human beings are also not perfect. So we have got to have certain error in everything. Each method has some errors. Of course, error varies from one method to another. Then we have error due to some other factors like the temperature variations. Variation in temperature not only changes the values of the parameters but also brings changes in the reading of the instrument. That is very important. So we have to maintain a uniform temperature whenever we are doing certain experiment or whenever we are taking a reading on a certain instrument. For a consistent error, the temperature must be constant. Then the B is the effect of the time on the instruments. There is a possibility of change in calibration error in the instrument with time. Like if I give you an example, if we have got a wire and we are hanging it from two ends of the wall. After some time, you can see that there's a certain creep. The wire has changed shape, and that's why the error has come in. So with time also error comes in, and that is called the aging of the instrument. Then C is the effect of external electrostatic and magnetic fields. We know that our atmosphere or environment is filled with these kind of magnetic and electrostatic fields, so they also influence the reading of our instruments, and these effects can be minimized by proper shielding. So there are certain kinds of shielding for reducing these kind of errors due to the electrostatic and magnetic fields. Then the D part is the mechanical error, like due to the friction. Friction, we all know that it causes wear and tear. So friction between stationary and rotating parts and residual torsion and suspension wire cause error in instruments. So checking should be applied. Generally, these errors may be checked from time to time. After talking about all these errors, we come to the random errors. So after corrections, after applying all the corrections, like we have seen the systematic errors and we have seen the gross errors and we have avoided all of them, we come to a certain error which is generally non-avoidable. So after corrections have been applied for all the parameters whose influences are known, there is left a residue of deviation. These are the random error and their magnitudes are not constant, because we cannot make out how much it is. How much is the error? That's why it is never constant. It may be, suppose, like in case of force 2 Newton, or it may be 0.02 Newton. It may vary because it is random. Persons performing the experiment have no control over the origin of these errors. Anybody who's doing the experiment or the observer, he has no control on these kinds of errors. And these errors are due to so many reasons, like for example, noise, if there is certain noise, and then if the worker or the experimenter or observer is undergoing fatigue, he is very tired, then also he may make mistakes. So these errors may be either positive or negative. To these errors, the law of probability may be applied. Generally, these errors may be minimized by taking average of a large number of readings. We have to take a large number of readings and then we have to get the average to minimize these kind of random errors. Now we talk about accuracy and precision. I have earlier also mentioned in the slide that our measurement should be very accurate, or it may result in catastrophic failure also of certain instruments or certain things. So that's why accuracy and precision are very important. So what is accuracy? Accuracy of measurement is defined as the deviation of measured value from the true value. Like suppose a certain weight is there, and weight has a value 5 kg. Okay, then if I am getting that 5 kg value every now and then after measurement, then it is very accurate. That instrument is very accurate. Otherwise, if I am getting, suppose, sometimes 6 kg, sometimes 7 kg, sometimes 8 kg, sometimes 4 kg, so that instrument is not accurate because it is moving away from its true value. Its true value is what? 5 kg. But it is given, every time I am measuring, it is given different readings. So then it is not an accurate instrument. Similarly, precision is there. Precision is that precision of measurement is defined as the deviation of different readings from the mean value. Like I said, if the mean value is 5 kg, okay, and you are getting say 7 kg, but you are getting that 7 kg in every reading. You measured for the first time, you measured for the second time, for the third and fourth time. Every time you are getting 7. So you are not getting close to the true value, but you are getting the same reading. So your instrument is precise, but it is not accurate. Another example can be like a dart game is there and you are throwing the arrows towards the center of the dart game. the center of the circle. So if you are hitting that center every now and then in different approaches, then it is correct, it is accurate. And if you are throwing the dart and it is not hitting the center of the circle, but it is hitting somewhere else, but you are hitting that point where you are hitting at the first time every now and then, that is precise but not accurate. So that is the difference between accuracy and precision. Meaning in precision, consistency is there, but accuracy is not there. Then we talk about the calibration of the instrument. So calibration of the instrument is done to find its accuracy. Before using an instrument, particularly a new one in a measurement system, it is required to calibrate it to find the accuracy, precision or uncertainty of the instrument. And how it can be done? It can be done by comparing that particular instrument with, first of all, a primary standard instrument, or second method can be by a secondary standard instrument having very high accuracy, meaning which has been calibrated before and we know that it has high accuracy. And the third way is by comparing it with a known input source. And an example for this can be a flow meter. Like we can compare it with a standard flow measurement facility of the National Bureau of Standards. Then the second method can be we can compare it with another flow meter which is very accurate. And the third method can be direct calibration with the primary measurement, like we are going to weigh a certain amount of water in a tank and then record the time elapsed to fill that amount of water in the tank. So in that way we can calibrate it also. So there are three methods for calibrating a particular instrument. So after talking about all these things, we will now come to error analysis. First of all, error analysis on common sense basis. So one rule of thumb can be that the error in the result can be equal to maximum error in any parameter used to calculate the result. Suppose there are three parameters, x1, x2 and x3. And the maximum error in x1 is say certain percent like 2%. Similarly in x2 it is 3% and x3 it is 4%. So maximum error in these three independent variables x1, x2, x3 is 2, 3 and 4% respectively. And we are going to take this maximum error. So what will happen? That we are going to get the maximum error in the instrument. So the error cannot go beyond this particular value. So this is one method of doing the error analysis. Another common sense analysis is to combine all the errors in the most detrimental way. So whatever worst can happen, we will take it. Okay, and that way we will be able to avoid the worst possible scenario, and we will be able to get the maximum error in our final result. So now we talk about uncertainty. In certain things like in experiments, it is better to talk about uncertainty rather than error, because there are random errors also and there are certain errors which are beyond our control. So that's why we have to say uncertainty instead of error. Like for example, here it is given that this pressure measured which is given as 100 kilonewton per meter square plus minus 1 kilonewton per meter square. So this plus minus 1 kilonewton per meter square is the uncertainty in the pressure that is being measured. So when the plus or minus notation is used to designate the uncertainty, the person making this designation is stating the degree of accuracy with which he or she believes the measurement has been made. If a very careful calibration of an instrument has been performed recently with a standard of very high precision, then the experimentalist will be justified in assigning a much lower level of uncertainty to measurements than if they were performed with a gauge of instrument of unknown calibration history. So then that means we have to be very accurate in our measurement. Then only we can say that our uncertainty will be of lower value. So to add further specification of the uncertainty of a particular measurement, two scientists named Klein and McClintock proposed that the experimenter specified certain odds Odds meaning like if you see a cricket match, so there's a betting going on. What is the odd of that particular team winning, or like that thing? So like suppose I am giving an odd of 20-1, that there are chances of winning of 1% if 20 things are there. Okay. The above equation like pressure I showed you. So there's an odd of 20-1. So we will be using this thing. In other words, the experimenter is willing to bet with 20-1 odds that the pressure measurement is going to be within plus minus 1 kilonewton per meter square. It is important to note that the specification of such odds can only be made by the experimenter based on the total laboratory experience. So suppose a set of measurements is made and the uncertainty in each measurement may be expressed with same odds. And these measurements are then used to calculate some desired results of certain experiments. And we wish to estimate the uncertainty in the calculated result on the basis of the uncertainties in the primary measurements. So what are the primary measurements then? There are certain independent variables, like I told you earlier, like we can say x1, x2, x3 up till xn. So suppose there's a variable r that shows us the result, and it is dependent upon x1, x2 till xn. So there will be an uncertainty in the result, and that will be referred as W with a subscript R, okay, WR. And the uncertainty due to the different uncertainties in the various independent variables x1, x2, x3, xn, it will be given as W1, W2 till Wn, okay. And then if the uncertainties in the independent variables are all given with same odds, then the uncertainty in the result having these odds is given as WR, meaning W with the subscript R will be equal to del R by del X1, meaning the result which we have got R, that will be differentiated with respect to the first variable and it will be multiplied with W1. That means the uncertainty in the first result W1 due to the variable X1. Similarly, and it will be squared up. Then for the next one, meaning differentiating the result R with respect to the second variable X2 and multiplying it with W2 and squaring it. And further we will go on doing these things till we have reached to the n variable. And when we add up this thing and square root that thing, then we will get the uncertainty in the final result. That is referred as WR. Okay. So we do statistical analysis also of the errors. Like here the formulas are given. The first one is about the taking the average. You have got certain number of variables which are referred as xi, meaning x1, x2 till xn, and you do the average of that. That is one thing. Then we also do the standard deviation. In the second formula you can see in the slide, that is 1 by n, sigma I is equal to 1 to n, xi minus xm whole square and the square root of the whole thing. So this is known as the standard deviation. And the third one is the geometric mean. That means x1, x2, x3, xn to the power of 1 by n. And it is very appropriate to use a geometrical mean when studying phenomena which grow in proportion to their size. And this is very much applicable to biological processes because there is growth like this depending on the geometric mean and the exponential process. So that's why for biological processes this type of analysis is done. Then the analysis of limiting errors. Manufacturers of any equipment give guarantee about the accuracy of the equipment with some limiting deviations from the specified accuracy. Most of the measuring instruments are guaranteed for their accuracy with a % deviation of full scale reading. So that's what we give, and the limiting deviation from the specified values are called the limiting error or guarantee error. Okay, so in today's session we have discussed about the measurement and metrology, and further we saw the various kinds of errors that are there in the instruments and how we can avoid it. So I think that you have gained certain knowledge about these aspects of measurement and metrology, and in the further sessions we will see the details of other things which will come up. So thank you very much learners for listening. Thank you.